Okay, so raise your hand if you have not ever been in a physics class. Okay, so there's a few of you that haven't been in physics, didn't really learn vectors. You should have learned vectors in geometry, the basic vectors, but some of you will know most, hopefully all of this, but I know that some of you will not. So let's first talk about a vector. What does a vector have? Magnitude and direction. Very good. So it is a quantity that has both magnitude, which that is just your size or length, and direction. Okay. So a vector can be represented geometrically as a directed line segment. It looks like a ray when you're drawing it, but it really is a directed line segment because the ray has the arrow because it's going on forever. A vector has the arrow because it's showing you which direction you're going on. So here's P. P is where we start from. So this is called the initial point. It is also called the tail. Then Q is where we end. So that is the terminal point. Also called the tip. Okay. So vectors are denoted using an arrow symbol. So you write it like it's a ray. So vector PQ above can be named as, because it has the capital P, the capital Q for the beginning and the end, because those are points, and then there's this lowercase p here. There's a blank here because PQ disappeared, but we're going to have a capital PQ with the arrow over it to denote that it is a vector. Or it could just be the lowercase p with the arrow. Or it could be a bold-faced lowercase letter, which is really just used in typing or like print. Obviously, if you're writing it out, you would probably need the arrow so you could show that it was actually bold. What do you think the magnitude of a zero vector is? 0. Okay, so a zero vector has a magnitude or a vector with magnitude 0. Okay, that's what a zero vector is. So some types of vectors, we have parallel, equivalent, and opposite. So let's look at what those are. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. So they don't have to be the same length, but they do have to be parallel, basically. That's why it could go in the same or the opposite direction. So it could look like this. Those are going in the opposite direction, don't have the same magnitude, and then we can say A is parallel to B. Equivalent vectors, what does the word equivalent mean? Equal. Basically, it's a fancy word for equal, or the same. So they have the same magnitude and direction. So that would look like this. And then we can say vector M is equivalent to vector N. Then opposite vectors have the same magnitude, but opposite directions. And to show the opposite of a vector, you just put a negative in front of it. So the opposite of vector A is negative A. So same magnitude, but opposite directions. It look like this, U and V. So then we can say vector U is equal to negative vector V. That's how we show that they're opposite. Okay. Any questions at all? All right. So We've got these vectors scattered all around here. So let's start with, it says use the graph below to classify each pair of vectors. So A and E. Here is A. Here is E. Do these two have the same magnitude? Yes. And so what would these be called? Are they equivalent? Do they have the same magnitude and the same direction? No. So what does that make them? Opposite. So these are opposite vectors. Okay. So then I and F. Here is I. Here is F. Do these have the same magnitude? Yes. Do they have the same direction? Yes. So what are they? Equivalent. Good. All right. Then D and E. So here's D, and then we're using E again. Do they have the same magnitude? No. Do they have the same direction? Yes. So what are these? Parallel. Very good. All right. Then B and G. Do those have the same magnitude? Yes, they do. Do they have the same direction? No. Do they have the opposite directions? No. So this is none. They're just two vectors. They don't have a special relationship at all. And then C and H, same magnitude? Yes. Same direction? No. Opposite direction? Yes. So that makes them opposite. All right. Any questions about the very basics of the vectors? We all good? All right. Then grab your other page. And let's talk about component forms of vectors. So as you could see from what we just did, vectors can be anywhere in the coordinate plane, and we're back in the rectangular coordinate plane out of polar. But if it's in standard position, so this vector here is in standard position, that means that initial point is on the origin. Okay, so standard position is when the initial point what's another word for initial point? Tail. The initial point or the tail is at the origin. Okay, everybody good with that? So if it's at the origin, so if a vector v is in standard position with our terminal point here, our terminal point is right here and it's AB, then the component form of vector v is that the vector equals, and we use the pointy brackets, A, comma, B. A vector gives us distance and direction, but it does not give us location. If it's at the standard position, so we're here at the origin, then it does give us the location of the terminal point, but the vector could really be anywhere. Okay? And just like anything else, since we're starting at the origin, and that's at AB, I can make myself a little right triangle here. This is A, this is B. But instead of worrying about just the point AB, the vector is actually the purple arrow. It's that thing there. So the magnitude and direction angle theta of a vector given in component form can be used to find the following. So the magnitude or the length of it, it looks like a double absolute value. Okay, that means magnitude. What could we do with that triangle to find the length of that vector? Pythagorean theorem, right? So a squared plus b squared equals the magnitude of v squared. So I would just want to take the square root of that. So the magnitude of v is equal to the square root of a squared plus b squared. Isn't that exactly how we found r for polar? It's the exact same thing, right? Okay, so then I need the direction angle, theta. Well, if I have A and B, that's opposite or over adjacent, so theta is equal to the tangent inverse of B over A. Isn't that exactly how we found theta? when we were doing polar? Yeah, because we're basically doing the same thing. It's just in the rectangular coordinate plane. But it's what we did in polar. We went, what is the angle and how far do I go out from the pole, right? That's exactly what's happening here. Okay, it's just in the rectangular coordinate plane. Right, we good? All right, so we're going to find the magnitude and direction angle for each vector. Now, in polar, we were doing radians, and with vectors, we're back to degrees. So really, you could use either one and either one, but the majority of the time when you're using polar, it's going to be in radians. But in the majority of the time with the vectors, the more application-based stuff, you're using degrees. So we want to make sure these calculators are in degrees. So to do that, you're going to turn it on, shift mode 3 for degrees. Then you should see that little box with the capital D up at the top. It's real tiny though. So we're good. Shift mode 3. All right, so we're going to find the magnitude. So so this is, remember, in AB, and just like when we solved trig equations with the calculator, we had to think about what quadrant we were in, and even when we did this polar stuff, we had to think about what quadrant we're in. So even though this vector could really be anywhere, it's pointing to, if I do 7, 24, you think about it in standard position, pointing towards the first quadrant. So I'm in quadrant 1, because our quadrants are going to matter. So we're going to find first the magnitude. So the magnitude of R is equal to the square root of 7 squared plus 24 squared. Now, if you actually write out this part right here that tells me you know what you're finding and what the notation is and what you're actually doing, then you can type that in the calculator and let the calculator give you your answer. So you can type it in just like that, square root of all that. Then the magnitude of R is going to be what? 25. All right, so then let's talk about why we care about the quadrants. So just like when we solved trig equations with the calculator, we are going to find alpha first, our reference angle. Now, when we solved those trig equations, we were using radians. And so when we found quadrant 2 was pi minus alpha, right? But now that we're in degrees, what's it going to be? What's pi in degrees? 180. It's 180 minus alpha. So quadrant 3 will be 180 plus alpha. And the fourth quadrant will be 360 minus alpha. So it's the exact same thing. We're just in degrees, not in radians. Okay? Exact same concept. So let's go back over here and find theta. Theta equals the tangent inverse of 24 over 7. So when I put that in the calculator, remember that gives me alpha. So go ahead and do that. You should get 73.740. And since alpha is your reference angle and it's always in the first quadrant, and we're in the first quadrant, this is your theta. And you're done. What questions do you have? All right, let's do number 2. What quadrant would number 2 be in? Third. Okay, so we're in quadrant 3. So I'm going to first find the magnitude of n. It's going to be equal to the square root of -3 squared plus -1 squared. Now when you square those numbers, what's going to happen? They become positive. So when I'm showing my work and substituting things in, this is what I write down, but I know that when I square it, it becomes positive, so in my calculator, I'm not hitting the negative buttons so that I don't have to worry about parentheses and all that other stuff. Make sense? You're totally safe just using the positive ones. Then you should get the magnitude of n equals what? Square root of 10. Everybody good so far? So then theta is equal to the tangent inverse of -1 over -3. And just like when we solved equations with the calculator for the trig equations, we are only putting the positive numbers in the calculator because we want to get alpha. even though that would become positive anyway, even if it wasn't, don't worry, just put in the tangent inverse of 1/3 so that we get alpha to be 18.435. And then because I'm in quadrant 3, what am I going to do with alpha to get theta? Add it to 180. You probably don't even need a calculator for that, right? That just makes that 198.435 degrees. What questions do you have? Anything? Alrighty. Then you do number 3. All right, what did we get for the magnitude? Good, 4 squared of 13. And aren't these calculators nice to just simplify that for you? It's pretty awesome. All right, so then alpha, we should get 56.310. Do you agree with that? Is that positive or negative? Positive, because you only put the positive numbers in, right? And then since we're in quadrant 4, what do you do with this number to get theta? Subtract from 360. Good. So we get 303.690 degrees. Everybody okay with that? Any questions at all? We good? Awesome. All right. I don't think we need to do number 4, but we're going to talk about it real quick. What quadrant would this be in? Okay, so we're in quadrant 2, and then when we take the tangent inverse and we get alpha, what do we do with alpha to get theta? Okay, so good, we'd do 180 minus alpha for that. Okay, makes sense? All right, so let's talk about what happens when it's not in standard position. All right, so because remember your vectors can be anywhere, but we can also slide them anywhere we want all the way around or translate them anywhere we want, because they don't give us a location, they just give us distance and direction. So if we want them in component form, we have to think about it being at the origin. So to find that, let's see, what do I call this vector B? If I have these two ordered pairs, this is going to be equal to, the x value is x2 minus x1, and the y value is y2 minus y1. So it's just the difference in the x's and the difference in the y's. That's all it is. So CD, vector CD, they give us the 2 points, right? And it has to be that it ends at x2, y2, or yeah, x2, y2. So it has to be d minus c. It can't be c minus d. So vector CD would be equal to 6 minus 3, 3 minus 5, which means that CD would be 3, -2. That would be the component form. Okay. Questions about that? All right, look at number 6. Do you have enough information to do number 6? No, why not? Yeah, because B and it's not S. So we're going to make B into S because I don't even know why that's B. It wasn't meant to be a trick. You go ahead and find the component form. -7, -9. And remember, these are pointing brackets. They are not parentheses. Parentheses would mean it's a point, and it gives me a location. This gives me a distance and a direction. Okay, we good? Awesome. So this next section, we're supposed to give the component form, the magnitude and direction for each vector. And so I have vector AB, and I have the 2 points that I need, so I can easily find my component form, and that means that vector AB is going to be equal to, so this would be -4 minus 9, which is -13, and then -1 minus a -3 would give me a +2. Okay. So then after that, I don't need these anymore. I'm just working with my component form to find the magnitude. So the magnitude of AB is equal to the square root of -13 squared plus 2 squared. And remember, showing your work is one thing. When you put it in the calculator, you can put those in as positive. That way you don't get yourself all mixed up with parentheses and whatnot in there. So then what's the magnitude? Square root of 173? Okay, so my direction angle. Theta equals the tangent inverse. And it's probably not a bad idea to just mark these out so you don't accidentally use those numbers somewhere. Excuse me, because we're going back to that component form. And this is going to be 2 over -13. So that's going to give me alpha. Let's go ahead and find alpha. .746. Okay. What quadrant are we in? 2. We're in quadrant 2. So what am I going to do with alpha to get theta? Subtract it from 180. Good. And that's going to give me 171.254 degrees. Any questions at all? All right, so number 8 didn't give us these numbers, but it gave us the vector on the grid, and so we could find those numbers and do that math, but we could also just count. So vector C, right? So here's where I start from. So to get to here, I'm going to have to go to the right. 1, 2, 3, 4, 5. So that's my x value. That's a +5 because I went to the right. Then I'd have to go down 1, 2, 3, so that's a -3 since I went down. Make sense? All right, you finish this one up. Find the magnitude and direction angle. Okay, so what did we get for the magnitude? Square root of 34. Very good. What do we get for alpha? 30.964. What quadrant are we in? Fourth. So that vector is sitting up there in the first and second quadrants, right? That's not what we care about with the quadrants. What we care about is if this was where the origin was, then we'd be pointing towards that fourth quadrant. So we're in quadrant 4. So what do I do with alpha? Subtract it from 360, and it gives you 329.036 degrees. So again, just like in polar, it's how far from the origin, and the angle gives you the rotation to get there. We good with that? What questions you got? Okie dokie. So let's talk about equivalent vectors again. It says vectors are equivalent if and only if we know they have to have the same magnitude in the same direction. That means they have to have the same component form. So we can use the component forms to determine whether A, B, and C, D are equivalent. So for vector AB, let's find the component form. That's our pointy bracket form, right? -7 minus a -3 would give me a -4. -2 minus 6 is -8. That by itself doesn't tell me anything. I have to find CD. That would be -1 minus 3, that's -4. And then -9 minus a -1 is -8. So do they have the same component form? Yes, they do. So vector AB is equivalent to vector CD. And the whole thing is your answer, showing that you found the component forms and then making that statement. We good? All right, you do number 10. Are these vectors equivalent? No. So I still have to make that statement. So now I'm going to say AB is not equivalent to CD. Okay. Any questions at all? We good? All right, so your assignment is in Delta Math. You have about 15 minutes left, so go ahead and get to work.